Among the non-prehensile manipulation, the robotic pushing is one of widely studied skills that are applied in various tasks in nowadays. Despite this potential, robotic pushing still faces several challenges due to hybridness and uncertainties of the pushing system. The main scope of this paper is to develop the dexterous goal-oriented robotic pushing framework by allowing pushers free motion. So, we first derive the contact-aware pushing motion model, called C-GVMM, that describe the relationship between the pusher's velocity and slider's motion. First, we have already know the relationship between the contact forces and slider's motion. Here, the contact forces are constrained by a contact mode dependent constraints with a sliding rates phi dot, and it can be rewritten as follow. For a single contact case, this decision plane can be formulated as follow, and it describes the corresponding contact mode from the given pusher's velocity. We validate this contact mode decision plane using MIT pushing dataset, and the results show that this formulation can capture the reliable contact mode from given pusher's velocity. For a goal-oriented robotic pushing, we utilized a Model Predictive Path Integral as a goal-oriented pushing motion generator. Here, we adopt C-GVMM as a prediction model so MPPI can roll out both pusher and slider's motion by allowing various contact mode without any predefined contact mode. Also, we leveraged the UKF-based online model estimation to overcome the uncertain object properties which often face in real-world setting. These videos show the result of the numerical experiment under uncertain object properties. Here, we can observe that the proposed that iteratively update the model parameters behave as more optimal than baseline which use wrong fixed model parameters. Through these numerical experiments, we can conclude following two things. First, the MPPI-based pushing can behave as a goal-oriented motion generator with a dexterous pushing motion. Second, the uncertainties on the physical properties really can affect the pushing behavior, and the combination of the MPPI-based controller and UKF-based online model estimation can overcome these uncertainties. To demonstrate the proposed goal-driven robotic pushing framework can work in real world, we also performed real robot demonstration under unknown parameter scenarios. As shown in these videos, the proposed also worked well in real world, and we can observe the robot move freely in the workspace with a contact-rich behavior. Then, we performed tableware cleaning demonstration to show how the proposed dexterous goal-oriented robotic pushing can be utilized in real-world application. In conclusion, the contributions of our work can be summarized as follows. First, we propose a contact-aware pushing motion model that automatically infers contact modes and validated using MIT pushing dataset. Next, we achieve goal-oriented robotic pushing with dexterous and accurate pushing motion. Finally, we validate the effectiveness of our approach through comprehensive numerical experiments and real robot demonstrations.